So a key concept in thinking about MSTs turns out to be this concept of safe and unsafe edges. But first, in the following, we're going to assume that the weight of the edges are all distinct. This assumption is easy to remove, as we will see later on. And a key concept that we need is this concept of a cut. So what is a cut? You take the graph and you pick a subset of the vertices S. You look on the complement set of vertices, all the other vertices in the graph, V minus S. And the cut is just all the edges that go across. One endpoint is in S, the other end is in the complement. Okay, so this is called the cut. You see a picture here in the top on the right side. The intuition behind the idea of cut is that those are all the edges you need to cut to separate this group of vertices from this group of vertices. So, a very useful definition. And we usually would use this notation, S and V minus S as the set, and this concept just lists all the sets UV, so that U is in S and V is in the complement. A cut edge is crossing the cut. It goes from one side of the cut to the other side. So that's the concept of a cut, and intuitively cuts are important for MST because every cut must be bridged. The minimum spanning tree must pick an edge to get across the cut, otherwise the tree compute would be disconnected, which is of course impossible. Okay, so a safe edge is an edge such that for some cuts it's optimal. Right? You look on an edge E, you can find some cut that contains this E, and this edge is the cheapest among all the edges in the cut. Right? So there might be a lot of edges in the cut, but this is the cheapest one. So an edge, such an edge is called safe. Intuitively, a safe edge is an edge that you would like to put in the MST because it bridges the cut and it does it very cheaply, right? It's the cheapest you can do, and we are cheap people. We would like to build cheap spanning tree. On the other side, and this is less intuitive maybe on first sight, an edge is unsafe if there's the edge E, if there is a cycle in the graph which contains E such that E is the most expensive edge in the cycle. And the intuition behind this definition is that if an edge is unsafe, you would prefer not to put it in the MST because it's expensive, right? The cycle is essentially a witness to the fact that this edge is too expensive and you should not include it in the MST. That's the intuition. We will see how this intuition comes true shortly. But first, let's prove a claim. Every edge in the graph is either safe or unsafe. Okay, so let's try and prove it. So let's look on any edge E and assume that its endpoints are UV. And now we're going to look on the graph G, but take only, we still have the same set of vertices, but we're going to take all the edges such that the weight is cheaper than the weight of W, right? So those are all the edges that the price is smaller than the price of E. In particular, the edge E itself is not going to be in this graph, right? So E is the cheapest edge not yet in this graph, because we're assuming that all the prices are distinct. And now look on the endpoint of this edge, right? We have the endpoint E. It has two endpoints X and Y. Okay, and we look on this graph that we built, right? And okay, maybe this is a bit uninteresting. well, okay. This has to say same, not some. If it's in the same connected component, right, like here, right, notice that this graph is not this bizarre graph is not necessarily a tree, but it's a graph. And the important thing is that if x and y are in the same connected component, then there is a path. This is g smaller than w of e. Then there is a path in this tree between x and y, right? E itself is not in the graph. So if I take this path connecting x and y in this graph, then all those green edges that I drew, those are edges in the graph where all the weight of the edges are smaller than the weight of E. So this green path together with the red edge, E, form a cycle where E is the most expensive edge in the cycle, namely E is unsafe. So that implies that E is unsafe in this case. Okay? Maybe the more interesting case might be the complement case. So the complement case is where you computed this graph and x and y x and y are in two different connected components of this graph. Let me maybe use the red color again, just to make sure that we're on the same color. Okay. Now, if they're in two different connected components, then just take the connected component containing x in this graph. We are getting a set of vertices S, right? And observe that E, this edge E, is not in the graph, right? But it's the cheapest edge not inserted into a graph by definition and by the assumption that all the weights are distinct, which means that the edge E is going to be the cheapest edge in the cut between S and all the other vertices in the graph. Namely, E is going to be safe. And we are done, right? We proved that the edge E must be either safe or unsafe. So that's it. That's what the claims say. Okay, so again, safe edges are the cheapest edge in the cut. So if you look on this cut, for example, the safe edge is going to be this because its weight is 3. Or at least I hope so. Yeah. Now, very importantly, the number of cuts in the graph is exponential, so an edge E might be safe for a large number of different cuts. That's completely fine, completely legal. An edge is unsafe if it's the heaviest edge on the cycle. In this case, clearly this is this edge. Okay, and again, an unsafe edge might be unsafe for a large number of cycles because the graph might contain an exponential number of unsafe edges. Okay, so let's look on this example. And the claim is that all the red edges are safe. So let's see why this is true. So if we take the vertex 1 against everybody else, the cut, this edge is the cheapest edge, right? So this edge in this should be in the cut. Similarly, if you take this vertex, this edge is the cheapest edge connected to it, so it's safe. So we verify that this and this are safe. This edge is safe if you look on the cut between this vertex and all the other vertices, right? So this is safe, good. If we take this edge, if we take this vertex, then this edge is safe. If we take this vertex, then this edge is safe, right? The vertex 5 against all the other vertices, the edge of price 17 is the cheapest. So we verified all the edges are safe except for this edge here. For that we will take this cut. Okay? So this cut, if you look, all the edges, there is an edge of 28, 25, 16, 9, 15. So this edge is indeed safe. So indeed we proved that all those edges are safe. All the edges are safe. Now let's verify that all the other edges are not safe, the non-red edges. And that's very easy, right? Because what we're going to do is we are just going to add an edge, each one of those edges, let's add them to the red graph. So if I add it to the red graph, I get a cycle. And magically enough, 28, 23, 1, 9, 3, 17, for example. 28 is the most expensive edge, so this is unsafe. Similarly, if I add this edge, then the edges on this cycle are going to be this and this, right? And as such, 36 is more expensive, so this is indeed unsafe. And we can continue in this fashion. You can verify in a similar way. If you put every edge in, together with the red edges, you will get the red path and this edge, and it would be a cycle that showed that the edge is unsafe. This is not coincidental. This is essentially a basic property, because if you look on this red subgraph, it's in fact the minimum spanning tree of this graph. And this is related to what I just told you, that safe edges essentially form the MST. So we will prove later on the following, that if an edge is safe, then it must be contained in every MST of the graph. And if an edge is unsafe, then it must not be in any MST of the graph, right? So safe edges are good, unsafe edges are bad. But it turns out that it's not only that, it's just that all the safe edges together, they just form the MST. And we will see later on why. We will prove this later on, not immediately now, these two claims.